Well, welcome to good evening to all those who are participating in this program. I want to firstly welcome all of you to the very first session of the Siyanqoba training program for seniors. A special word of welcome to two of our distinguished guests. One is Mr. Mark Ancelotti, who has been instrumental in doing a lot of work to get this program organized. And we have our friend from Limpopo. I'm not sure whether he's arrived yet. And more than that, we have the organizer from the South African Maths Foundation, the project manager, David Ramoboka. Welcome to all of them.
Thank you, Prof.
Let me congratulate all of you for having reached this milestone of your mathematical careers. To get into the second round and even the third round is quite an honor, because a very large number of people, students around the country, enter the first round. So I feel privileged somewhat to be addressing a rather august gathering of mathematics students who are enthusiastic, keen, and proficient in the subject. This program is meant for problem solving, and problem solving, as you know, are essentially non-routine problems. They are far more interesting than the routine problems that you do at school, but the kind of stuff that you have learned in primary school and in high school will hold you in good stead to solve problems, because they give you they are the tools, they are the machinery to which you can solve problems, symbols, equations, and the like. So with those few words, let me go straight to problem one. I trust that you have already received what I named as the problem book. The problem book has got problems for the juniors as well as the seniors, and the senior problems are on page 26 onwards in that problem book, and they are divided up into 9 sessions, because that is the number of sessions that we will be having. So today we are going to do session 1. So if you go to that, you don't have to do that now, then you will see which problems we are going to tackle. Those problems have got many more problems than the ones that we are going to tackle. I have selected maybe 8 or 9 problems from that list of maybe 10 to 15 problems for discussion purposes. The remaining ones are for your own improvement. You can try any of those problems which we haven't tackled, and be quite free to send me an email of your solutions to those, and I will look at them, mark them, and give you the solution. I may not mark them, but at least I can discuss something with you through by email. All right, so once again, it's just we are going to do those selected problems. Amongst those selected problems, there will be one which is marked in red. And today, the one that is marked in red for session 1 is problem number 5, I think. And that problem is, I would not discuss that problem. That is your assignment problem. You have to do only one problem for each session, and you have to do that problem, right? Make an attempt to write the solution in full, not just the answers. Write it in full, and scan it and email it. You'll get more information on that. Okay, that will have to be sent to your center manager, but at some time your center manager will explain more on that assignment problem. There is also a guideline document which I sent out. You will receive that. Please study it very carefully to know exactly what the terms of reference for this session, for this program are, especially the, uh, the various aspects of the program and what is expected of you. All right, so let's go to problem 1. I'll have to get a little bit used to. Okay, I trust that you all can see the screen. David?
Yes, I can see.
Okay, good. Okay, the very first question, what is the value of square root of, you got a square in brackets, plus the square root of another square in brackets? All right, so this may look like an easy problem, which it essentially is. So the question is, what do you mean by the square root of, just one moment, please. Sorry, I'm trying to get my pen to write. I should have sorted this thing out a little earlier. Sorry about this.
Prof, just click on the draw option there.
The draw, yeah.
And then it should give you an option for your pen and your pen color and stuff.
Yeah. I've done that, but it's not
Okay.
writing. There are 2 buttons on my pen. I think one of them I pressed it mistakenly. And my goodness, this is very bad. I'm sure we'll get this somehow.
But just take your mouse pointer to draw. Yeah, so all these options directly above your mouse pointer, go to the draw option. So go further left, all the way along next to the insert, between insert and design.
I'm at the draw option, and it's highlighted.
Okay.
Oh goodness, this has never happened to me before. I can't understand what the issue is. Sometimes there are 2 buttons on the pen, and sometimes I might click them in error, but when I press them again, they usually work. Oh, okay. Annotate.
Maybe just open the document. Open the document again, Prof. So close it and open it.
I've closed it and I'm opening it again. I must apologize to everybody. Not working still. Oh my goodness. This is really crazy. I have a writing pen, and I've been using this pen many times, and it always works, but I can't understand why it suddenly has given up on me.
But Prof, can you go to that draw icon? Just click it down so we can see what pen is there. It should show a drop-down menu.
Yeah, I can see the draw has got the pen and the straight line and squares and circles and all that. I can see that.
Okay.
And then I normally click on the writing one, right?
Yeah.
And that's what I've done. But it doesn't respond to any of the instructions on that
Okay.
for some reason. Oh God, this is really. Is there any other way? I don't know any other way of doing this.
Yeah, I wish I could talk you through it. I don't know what kind of pen you've got, whether it's a Bluetooth device. Yeah, how to re-enable your pen. There are times to switch on and off the touchscreen so you can enable the human interface device. But without seeing what's going on there, it's very hard to help you. Sorry, Prof.
Yeah. The thing is, I'm doing what I'd always do, and I've done this many times. I'm just concerned that maybe there is something wrong with the pen itself, which is a terrible thing because it's not easy to get this pen. Remote control.
Yeah, you see, I'm able to write on your screen.
Now you see. Now if I get to my pen, now you see it doesn't respond. Or you can write on my screen.
Yeah, I can write on your screen. Just
This is extremely frustrating. I have no idea what I should do now. Let's just get back to annotate.
I've given you back control, so you should be able to write there.
Yeah, so I'm using my mouse and my pen simultaneously. Oh God.
Metro nakhona uyathanda ukuphapha manje. Manje lana i-live yini? I-live man.
Sorry, young, yeah.
Now the pen is not even responding now. At least before it was. Let me just unplug it and plug it again. I'm unplugging my pen.
Sure.
Okay, it's some. Here we go. All right, we're on our way, guys. Sorry about that.
Brilliant.
All right. It is a good solution. We unplug and plug. You know, we know that rule, but we didn't apply it. Okay, guys, we are 20 minutes late, but I'm sure we'll be able to manage. So what I was saying is that when you have the square root of a square, this is not very light. Let me just change the color. Square root of x squared, your guess is that it's going to be equal to x. If you're asked this, what is the square root of x squared, you will say it's x. But if I ask you, what is the square root of -5 squared, you will not say -5. You will take -5, you square it, comes to 25, and you will say it's 5. So the square root of -5 squared is +5. Okay, the moral of the story is that the square root of x squared is either x or -x. The negative, provided the x itself is negative. If x is negative, then the square root of x squared is -x, because the square root is always a positive number. Very important. It's a function. It doesn't got two values, right? So the square root of any number is, you take only the positive value. Okay, so bearing that in mind, now the question is, if you take this first one here, right? The stuff that is being squared is square root of 20 minus square root of 20, or minus 21. Square root of 20 is approximately 4. 4 minus 21 is negative, you see? So the square root of this is not square root of 20 minus 21, but it's negative of square root of 20 minus 21. And in this case here, you don't have a problem because this is positive. So the square root of that object squared is itself. So now when you simplify this, you'll get 42. Okay. Can you see the board? Is the writing bright enough?
Yes, I can see it.
All right. Okay, because it seems to me it could be a little bit thicker. I'm not sure how to do that. Okay, so let's just get on to the next problem. By the way, if you do have a question, we have muted all of you. If you do have a question, put it in the chat box. And if you have time at the end of the session, then I will address those answers. But if we don't have time, then I will write to you separately and address it by email. Okay? I'll try to make that promise, but let's hope I can keep to it. So now we get on to the next problem. Okay, we're going on to problem number 4 now. Problem 4 states that for how many positive integers k does the equation kx minus 12 equals 3k have an integer solution for x? All right, so at a starting point, you have an equation and you want to solve. And you want to solve for what? You want to solve for k, right? We're not asking for the solutions for k, but the question is for how many? So we must make sure that you understand the question and answer the question. So we're not asking for the values of k, we're asking how many such k's there are. Well, the usual practice, whenever you're solving for an unknown, you bring all the unknowns to one side. So kx minus 3k is equal to 12. And then you can take k out. K into x minus 3 equals 12. Now, this is an equation where the symbols are not any real number, they are integers. And you have a lot of problems like this where the equation has got integer solutions. So 2.5 square root of 3 and so on are not allowed as solutions. So these are integer solutions. So you've got two integers multiplied to give you 12. Now, what does that mean? It means that k is a factor of 12 and x minus 3 is also a factor. With integers, you have factorization. That's a nice thing. You can't factorize a half, right? You can't factorize a square root of 3, but you can factorize a whole number. Even an integer, negative 12 also can be factorized, right? Negative 3 times 4 is negative 12. All right, so k is a factor. Now k is a factor of 12. So the question is, what are the possible factors? Well, you will say it's 1, 2, 3, 4, 6, 12. Make sure you count 1 and count the whole number. But here we're asking for integer solutions. Now these are positive integers. They are natural numbers. But negative numbers are also allowed in integers. So even negative 1 is a factor of 12 because 12 is equal to negative 1 times negative 12. See? So negative 1 and negative 12 are also factors. So you have to include the negatives as well as the positives in these factors. And the question is, how many solutions have you got? So the answer is 2, 4, 6, 8, 10, 12. So the answer is there are 12 values. Answer is 12. There are 12 possible values for k. All right. You can try any one of these solutions. Try, for instance, negative 4. Now let's just test to see if negative 4 is a solution. Okay, then you put negative 4 for k. And then negative 4 times what gives you 12? It has to be negative 3. So therefore, in that case, the x value is 0. So you do have a solution. Both of them are integers. And x is an integer. Right? The question is the integer solution for x. So both of them are integers. So if x minus 3 is an integer, then so is x. Because it's only 3 more than x minus 3. Okay, so the answer to this problem is 12. The next problem is your assignment problem. I marked it in red just to show you which problem you will have to submit, and the person who is in charge of your session, your group, will tell you more about that. So this is, in the meantime, you can try to solve this problem. Right? I'm not going to discuss it. You can think about it carefully and try to solve it. Okay. Hopefully, by the time we finish off, you'll have a better idea how to solve it. Okay, we'll go on to question 7 of session 1. A certain country has coins having values 1, 3, 5, 1, 3 or 5 cents. So you have a 1 cent coin, 3 cent coin, 5 cent coin. Now the question is, can one make a change of a 25 cent coin using 10 coins, each having a value 1, 3, or 5? The actual question in the problem book, I think there was an error there. Something was missing. Maybe the word 10 or something was missing. But so now the question is, now you have to use 10 of these coins. Is it possible to use 10 of these coins, each having value 1, 3, or 5, so that when you add everything up, you're going to get 25? Okay, so that is the question.
5, 15.
David, can you please just attend to this?
No, I'll take care of it, Prof. I'm busy with that. You just
Yeah.
continue.
Please don't talk. If you do, have your mic off, and we are manually putting your mic off because you disturb the rest of the crowd when you are also talking. Okay, so the question is now, can you use 10 coins here to make up? All right, now you can use a 5 cent coin, but then you only got 20 cents left. Now you'll have to use the others to see whether you can make up 20 cents and try them out. So you can try various ways of getting 10 coins to add up to 25. And so the question is, can one make a change? Right? All right. So the way to handle this problem is okay, suppose it can be done. Suppose it can be done. So you have 10 coins altogether. And we'll just call them, let's call them A, B, C, D, and so on. And going up to J. J is the 10th letter of the alphabet. So these values are going to be 1, 3, or 5. There are 10 of them all together. And they're going to all add up to 25. Right. Now the question is, is this possible? If you think you know the answer to the question, you can raise your hand and David will unmute you. All right, so let me just point out something. That 1, 3, and 5 are all odd numbers, right? So remember, all these are odd numbers. Now suppose I pair them off 2 at a time. I can do that because I've got 10. Hij. Right, so now you got these 5 numbers, because we are pairing them off, add up to 25. But remember, since both of them are odd, when you add 2 odd numbers, what do you get? You get an even number. Very important fact. The sum of 2 odd numbers is even. Right? The sum of 2 even numbers is even. But if you have an odd number and an even number, when you add them, then the answer is odd. But if they are the same, what you call parity means the evenness or the oddness. If they have the same parity, then the sum of those 2 numbers is an even number. Now you got 5 even numbers added. You can never get 25, because even numbers, when they're added, you're going to get another even number. Okay, so the answer to this question is no. Right. Now, if there were 10 marks for this question and you put on answer no, you'll get 1 mark for getting the correct answer. But you have to explain why your answer is no. And that requires a certain amount of language. And this is what we expect you to do in the assignment problem. You have to explain. You're not writing just an answer. You have to explain in detail how you solve the problem. So that is an important test, because when you do round 3, you are expected to write out the answers. So this will give you training to write out your answers in full, so you don't miss out any pieces of information, and you write it in a proper, logical way. Okay. While we're on this, there's mathematics involved with the even numbers and odd numbers. So how would you define an even number? Even numbers are 2, 4, well, even 0 is even. 2, 4, 6, 8, and the negative numbers. So how would you describe this? Even numbers can be described as 2 times n, where n is an integer. Now this is important. So a number is even. If you know that a number is even, you can, and you don't know what it is, you can say, let the number be 2n, where n is an integer. You must say where n is an integer, right? If you don't, then you are allowing n equals a half, for instance, which means you are saying 2 times a half is an even number, which is false. 2 times a half is 1, right? You have to say it's an integer. So even numbers are all expressible in the form 2n. So if you know how even numbers are written, then you can write down how odd numbers are written, because an odd number is always 1 more than an even number. So if a number is odd, you can write it as 2n plus 1, because the one just before it is an even number, and it will be like that. You add 1 to it, that gives you the odd number that you have in hand. So even numbers, there's a mathematical way of expressing even numbers. We're going to use that fact in the next problem, which is a problem that I'm going to take a fair amount of time to discuss. It is probably the most demanding of all the questions that we have in today's session. Let n be a natural number. A natural number means a counting number, a positive integer. 1, 2, 3, 4. Right? That's the difference between natural numbers and integers. Natural numbers are always positive. If the tens digit of n squared is equal to 3, then what is the last digit of n squared? All right, so you got some natural number, n, and you're squaring it. So you take, for instance, 11 squared. Here n is 11. And then it says that the tens digit, in other words, this number here, that's your tens digit. This is your units digit, tens digit, 100 digit. So this number here is equal to 3. So then what is the last digit of n squared? So n is not equal to 11 because the tens digit is not 3. All right, so we want to know what the last digit of n squared is. Okay, so we don't know what the number is. So but we know that the tens digit is equal to 3. So there are a couple of things that I'm going to say here, which are of general knowledge. Well, not general knowledge, it will be always useful in discussing square numbers. So let me just talk a little bit about square numbers. So square numbers, they've got some important properties which are used in these problem solving things. Right, so let's just look at the first few square numbers. We'll take n to be n. N is a natural number. Let's just take these n, 10. But the next one will be 11, 12, 13. They will be ending in the same numbers that we already have in this set. So any natural number will end in one of these. There are only 10 possible ways in which a natural number can end. And these are the possible ones. Now, if you square any number, like if you take 137 squared, I don't know what 137 squared is. But certainly I know what the last digit is. Because the last digit will be the last digit of 7 squared. See, 7 times 7. So the last digit, we don't know what this is, but the last digit will be 9. But we don't know what the other ones are. So you can always say what the last digit of any square is, because you only have to look at the last digit of the single number. So if I know what these end in, 2 squared is 4, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 0 squared. 9 squared is 81, so I put only the last digit. 8 squared is 64, I'll put the last digit. So now I know that n squared ends in any one of these. So the endings for n squared are 1, 4, 9, 6, 5. 6 is repeated, 9 is repeated, 4, 1, 0. So squares only end in certain numbers. Squares end in, we can include 0, 1, 4, 9, 1, 4, 5, sorry, 9, 5, or 6. So there are only 6 possible endings in a square. For instance, a square number can never end in 7, because no matter which number you take, and if you square it, this is going to end only in these, like what we have said here. It all depends on what the last digit is. So a square number can never end in 7. It's not here, not in this list, or 8, or 2, or 3 for that matter. So the square numbers can only end in one of these 6 numbers. So that's an important fact. Just remember 0, 1, 4, 0, 1, 5, 6, 9. Okay, those are the endings of the square. All right, so that's the first fact. Now, the other fact that I want to bring to your attention, the second fact, the second fact that I want to bring to your attention is the following. Let me just have a new page here. All right. If you take an even number and if you square it, then the result will always be a multiple of 4. Take, for instance, 6 squared, 36. 4 times 9. 10 squared, I'm sorry, 36. 10 squared is 100. That's 4 times 25. If you take any even number and square it, you are going to get a multiple of 4. Now, why is that so? Because, as I said earlier on, in general, if I take an even number and we are not giving it any specific value, we'll say let the even number be, as we said earlier on, 2n. That's how an even number looks, where n is an integer. Right. Now, if I square it, I'm going to get 4n squared. And this is 4 times, because n is an integer, n squared is also an integer, so it's 4 times an integer, which means it's a multiple of 4. So the lesson from this is that the square of an even number is a multiple of 4. Always. Right? So this is the statement here, the square of an even number sorry, my writing is not very good, is a, so you have to listen to what I am saying, a multiple of 4, right? Okay. So that's a fact that I needed to say. Now, what about the odd numbers? So if I have an odd number, if I square it, is there, obviously it's not a multiple of 4, but I'd like to know what happens when I divide by 4. Obviously, it would not be divisible by 4, but if I divide by 4, what happens? So let's take some examples. Take an odd number like, say, 3, 7, 9, 11, 13. Let's just take those and square them. 9, 49, 81, 121, 169. I'm sure you all know these first few squares. If I divide this by 4, the remainder is not going to be 0 because it's not multiples of 4. But let me look at the remainders. When I divide 9 by 4, the remainder is 1. 4 goes into this 2 times. Here, 49, if I divide by 4, 4 times 12 is 48. The remainder is 1. 81, 4 times 20 is 80. The remainder is 1. Here, 4 times 30 is 120. The remainder is 1. And when it comes to 169, there too you'll see the remainder. So I'm going to call this remainder divided by 4. You'll see the remainder is always 1. But the fact that if I proved this just for these 5 numbers doesn't mean that I can assume that it's going to work for every odd number. So square of an odd number I'm going to speak about now. Square of an odd number. I'd like to say it leaves a remainder of 1 when divided by 4. As I've illustrated in these 5 examples. So when you divide by 4, it looks as if you're going to have a remainder. But how do I know this is going to be true all the time? If I take 2,000, and if I square this thing and divide by 4, how do I know I'm going to get a remainder of 1? See? So very often we guess. But the guesses in mathematics, guesses are not allowed. Right? I know when you do patterns and so on, you just assume that the next one is going to look like this, right? Without even trying to prove it. But in real mathematics, when we are doing problem solving, you're not allowed. So how do you prove it? So now the general odd number, as I told you earlier on, is 2n plus 1. This is an odd number. All odd numbers look like this. And now what are we doing to this odd number? We are squaring it. Right. And now I'm going to divide this by 4. But I can't divide this by 4. Let's see what happens here. I get 2n plus 1 all squared. Okay, when you use the square rule, you get 2n all squared, which is 4n squared. Then you multiply these two, you get 2 times 2n, which gives you 4n. 2n times 1 is 2n, double it. Now you can write this as 4 into n squared plus n, like that, 4. You can take it out from this first 2, plus 1. So what happens here now? When you're squaring this, you get a multiple of 4 plus 1. Right? A multiple of 4 plus 1. So in other words, when you divide this number here by 4, right, 4 goes into this part here, and the remainder is 1. Can you see that? So you only got 4 times an integer plus 1. The remainder, when that number is divided by 4, is 1. Now that's a deep sentence. I'm going to repeat that. You got a multiple of 4 because this is an integer, right? So you got a multiple of 4 and you're adding 1 to it. So this number here, as we said, 4n is a multiple of 4. 4n plus 1 is a number which, when divided by 4, gives you a remainder of 1. Okay? So all numbers which leave a remainder of 1 look like this. See? So if n is equal to 2, for instance, 2 times 4 is 8 plus 1, 9. There it is. 9. So when you divide that by 4, the remainder is 1. Right. And if you want to talk about the numbers which leave a remainder of 2, they look like 4n plus 2. Or you have 4n plus 3. Right? So when you're dividing by 4, there are only 4 possible remainders. You're not allowed to have a remainder more than 4. You know, whenever you do division, this is what you do. That you divide, like for instance, if I divide 17 by 4, 4 goes into that, 4 times 16, remainder 1. So this number is equal to 4 times 4 plus 1. This is your remainder. Right? So 17 is equal to 4 times 4 plus 1. And it's of the form 4n plus 1. And you cannot say, when you're dividing 17 by 4, the answer is 2. Sorry, 17 minus 8 is 9. You can't say that when you divide 17 by 4, the quotient is 2 and the remainder is 9. You're not allowed to have a remainder which is more than 4. You know that. Right? So there are only 4 possible remainders when you're dividing by 4. In general, when you're dividing by 12, there will only be 12 possible remainders. Okay? And they are all the numbers from 0 up to 11. Okay, let me just, oh no, I just want to take these things out. Okay. So whenever you have a number of the form 4k plus 1, it means that when you're dividing by 4, divide that number by 4, the remainder is 1. And in the same way, we have other things, like for instance, if I had 7k plus 3, or 7n plus 3, whatever, this is a multiple of 7 plus 3. You can say something about this, provided n is an integer, right? Then this whole thing is an integer. So this integer here, when you divide it by 7, the remainder is 3. See? But if I had 7n plus 13, then you can't say that when you divide this number by 7, the remainder is 13. You're not allowed to give a remainder of 13. Okay? So in that case, what you do is, so when you divide 7n plus 13 by 7, what's the remainder? Then you'll say, well, look, 13 is too much. I must divide 13 by 7 first, and then you'll get just 7 plus 6. Then you have 7 comes out, 7 into n plus 1. And then plus 6. Now you got a multiple of 7, and you got 6 is smaller than 7. See, so you have to divide this by 7 to get a smaller remainder. When you divide this by 7, the remainder is 6. That's allowed. You're not allowed to have a remainder of 13. Okay, so that's the second fact. It leaves a remainder of 1 when you divide by 4. We've just proved it. In fact, I can tell you a little bit more. You see, n squared plus n, you can take n out as a common factor. And here you have quite a curious object. This is a product of two consecutive numbers. They are next to each other. 7 and 8, 9 and 10. And on the number line, when you have two consecutive numbers, integers, one of them must be even. The even numbers, they leapfrog two at a time, right? You keep adding two to get to the next. So when you got two numbers next to each other, one of them must be even. So the interesting thing here about this, a square of an odd number, is that it's 4 times, if one of these is even, so you got even times odd, but even times odd is even. Even times any number is an even number. The important fact. An even times any number is even. So you got 4 times an even number, which makes this thing here, that means this part here is 2 times something. So 4 times this is 4 times 2 times something, which gives you 8 something plus 1. So this is 8k, if you like, plus 1. So when you square an odd number, it actually has this form here. And we just said it means that when you divide this number and the square of an odd number by 8, the remainder is 1, not just by 4, right? You can try it out. There's the square of an odd number. Divide by 8. So what is the remainder? 8 goes in 9 one time. 48 plus 1. 80 is 8 times 10. 120 is 8 times 15. And 168 is 8 times 21. So if you square an odd number, it's always 1 more than a multiple of 8. All right, now that was quite a mouthful. And I hope you can remember some of those things at least. Right, so the square of an odd number is. I'm giving you a long lecture on the square of integers and what they end in, right? Now, one last thing, when you want to test something which to be a multiple of 4, what do you do? Right? How do you test divisibility by 4? Right? I'm sure you know this. You look at only the last 2 digits. If you have some number, 10-digit number, which ends 36, you just look at this and say, well, 4 goes exactly into that, therefore, this is a multiple of 4. Okay, so divisibility by 4, this is how you test to see whether a number is a multiple of 4. There's something more I can say, and that is actually, even if you don't have a multiple of 4 at the end, if you had, for instance, 27, right? Now, this is not a multiple of 4. But remember, this is 24 plus 3, right? So, therefore, this thing here leaves a remainder of 3. When you divide this number, any number, by 4, by looking at only the remainder of the last 2 digits, you can say what the remainder is when you divide the whole number by 4. When this whole number is divided by 4, I can say immediately that the remainder is 3. Because 27 is 24 plus 3, right? So you can say, you can even say what, you can take any number whatsoever, you can say when you divide it by 4, you can say what the remainder is. Of course, in the special case when there's 28, the remainder is 0, so it's a multiple of 4. Okay, so those are the 3 things that I want to say. And now to get to this question that we are looking at.
You seem to be muted. We can't hear you.
Prof. 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 Prof.
Can you hear me now?
Yes, now we can hear you.
Oh, all right. Thanks for unmuting me. Okay. Okay, we are looking at the last two digits of n squared. We know that the 10th digit is 3, so it could be any one of these. There are 10 possibilities. Because the question is, what is the last digit? Okay, but we know that the 10th digit is 3. All right. Now, this is a square number. And we said the square numbers can end in 0, 1. It can't end in 2. It cannot end in 3. Can end in 4. It can end in 5. And can end in 6, but it can't end in 7. It can't end in 8. And it can end in 9. So we've eliminated 4 of these 10 numbers. Okay. Right. Now, the second thing is it's a square number. Right? And we said that if it's an odd number, now I want to find out what the remainder is when you divide this number by 4. The remainder has to be either 0 or 1, because when it's even, it's a multiple. And if it's odd, it's at least a remainder of 1. So I want to divide n squared by 4 and work out what the remainder is when divided by 4. I can accept only the remainder 1 or 0. Okay, the remainder here, when I divide this long number here by 4, I told you need to only work out what the remainder is. The remainder for 30 is 2. I'm going to do this thing quickly. So when you look at the remaining numbers here, these are the numbers that you get are the remainders. Right? And none of these can be a square because the remainders, except this one. The remainder when you divide a number by, the square of a number by 4 is either 0 or 1, depending on whether the number was even or odd. So these numbers here are inadmissible for the square. You can't get remainders of 2 and 3. So there's only one answer, and that is 36. So the answer to this question is, the last digit is 6. There's only one possibility for the last digit. Okay, so that took a fair amount of time, but I hope you learned something about square numbers. So just to recap, square numbers can only end in 0, 1, 4, 5, 6, or 9. Secondly, the square of an even number is a multiple of 4. Thirdly, the square of an odd number is a multiple of 4 plus 1. It leaves a remainder of 1. In fact, the square of odd number, it is a multiple of 8 plus 1. It leaves a remainder of 1 even when you divide by 8. So those are important facts about square numbers. All right, so now we get on to the next question. Oh, okay, so I wrote some notes here, which I didn't use. Let's get on to the next question. Okay, so the next question is question number 9. How many integer solutions are there for the equation x squared minus 25y cubed equals 217? Now, what does this mean? It means that integer solutions mean I want x to be an integer and y to be an integer. And I want to find out which x and y will satisfy this equation, right? I'll give you no marks for identifying the year in which this question was set. All right. Now, how are you going to solve this problem? Okay, I'm going to exploit what I just said now, right? We know some facts about the square of an integer. So let's make the square the subject of this formula. X squared equals 125 y cubed plus 2017. Right, now I'm going to solve for x and y. So I can give different integers for y and try to find out for different integers which of these are actually squares. So you can try y equals 0 and you will get 2017, which is not a square. You can try y equals 1 and you see you get 2017 plus 125, which is something, 2142. And you see that's not a square and so on, until you come to some y, which gives you a square. Now, you will admit that this is a very long-winded process. Power of mathematics now comes to the fore, right? Because we can actually prove that it's impossible. It's impossible to find a y for which this thing is a square. Now, isn't that amazing? That's the power of mathematics. That means no matter what number I try, even an 8-digit number, I will never get a square in the. Okay, so how do we go around doing this? So I'm going to now show this is impossible. Claim. There are no solutions. We have to say in integers. In integers, that means you could have, if you don't give that constraint, I can put y equal to 1, and I will get something, and then x squared, and then I'll have a decimal. X squared is equal to something, and then you can say x is the square root of that, but it would not be an integer. Right? So we want both of them to be integers. So how do you go around proof of claim? I'm making a claim, and I'm going to prove it. So let's look at y. And focus on y. There are two possibilities for y. Either y is even, or y is odd. Now, why am I going in this direction? Because when I analyze x squared, I was asking the question about if x is even and x is odd, we know some facts about it. So let's try to look at what happens when y is even and y is odd. If y is even, let's take that case, y even. Let's analyze what happens to 125y cubed. Now y is even. So an even number, I can replace y by 2n. We said earlier on that the even numbers can be written as twice an integer, where n is an integer, remember. I'll put that in the side here. Always important to say what your symbols are. Right? Don't just throw in a symbol without saying what it is. So you've got this. Now 2 cubed, this gives 8, so it's 125 times 8n cubed. Right? And 125 times 8 is 1,000. Okay, so what does this mean? It means that 125y cubed, this thing here, is a multiple of 1,000. It's 1,000 times something. So in other words, this thing here, it actually ends. So x squared in this case is some number which ends in 3 zeros, because if you multiply any number by 1,000, like this one here, it will end in 3 zeros. And you're adding to this 2017, which means that when you, the last 3 digits of this will be 017. Because you've got, when you add a number like this, which ends in 3 zeros, and you put 2017, when you add them, the last 3 digits. So x squared is 2007. X squared is a number like this, which ends in 7. Now this is impossible, because we said a square can never end in 7. It can only end in 0, 1, 4, 6, or 9, or 5, 6, or 9. We said this earlier on. Right. So the conclusion from that is, therefore, y is not even. That's the conclusion. Because when we say y is even, we come to something which is impossible, right? Which means that the assumption that y is even is false, because you come to a false conclusion, right? That's an important fact. When you make an assumption and you come to a false conclusion, then you can say that your assumption is false. See? So therefore, y can't be even. So let's have a look at David, somebody has. Try not to make a noise. And if you do, make sure your thing is switched off. Okay, now let's take the case where y is odd. Now, in this case, it's quite clear. Well, I don't know whether it's clear, but when you multiply 125 by any odd number, it must end in 5. Right? 5 times 3, 5 times 5, 5 times 7, all of them end in 5. Right? So this first part here ends in 5 if y is odd. Right? And therefore, when you add 2017 to it, this ends in 5. So this must end in 2, because the last digit of this is 5. You're adding 2017. So the sum of the 2 last digits is 12. So it must end in 2. So again, you have a situation where this ends in, this number here now ends in 2. So x squared ends in 2. And we just said, we know that an integer can never, the square of an integer can never end in 2. So even this is impossible. So we have proven that whether whether y is even or y is odd, you're not going to get a solution. That means that y can't be odd. So y can't be even, y can't be odd. Now that's crazy. And the reason for that is that we put down an equation like this as if there are solutions. So there are no solutions. It's impossible. Okay? So that's the solution to that problem. As I said, if you've got any questions or anything like that, you doubt, put it in your chat column. I've got 2 chats there already, and I will address them at the end of the session if I've got time. Otherwise, I can write to you, because if I have your name, then I have your contact details, and I can write to you and tell you, answer the question if it's not already been answered. Sometimes we might have answered the question later on. Okay, so now we've got this problem here. An ant lives on the surface of a cube. Okay, now you've got a little bit more complicated thing. You've got a cube here, right? So the ant, this cube has got 2 points on it, or actually X, Y, and Z. X, Y, and Z are 3 points on the surface of the cube, right? They're all, these 3 faces meet at this single point here. The end travels between X, Y, and Z. X to Y, and then from Y to Z, along the shortest paths between each pair of points. So you travel from here to here in the shortest possible way, right? And here to it travels, takes the shortest possible pathway from Y to Z. But it's crossing a vertical line, remember? And here it goes in, it crosses this horizontal line, and it goes to another plane. Because this is a vertical plane, and this horizontal plane. So it crosses it, but the path that it takes is as short as possible. All right. Now the question is now, what is the sum of the 3 indicated angles? You got 3 angles which are indicated, namely, you've got at X there's an angle here, at Y there's an angle, and at Z there's an angle. These need not be right angles. You can see here, it's like an acute angle. But we don't know. You're not asked what these angles are. You're asked what is the sum of these 3 angles. Right? So it's quite a tricky question, but we have to try to see, what do you mean by the shortest path? Right? What is really the shortest path? So what I do here is, let's just look at X and Y. Right? If I'm going to take the shortest path from X to Y, right, I take the face, the top face of the cube is this flat face, right? And then I kind of lift it up to make the whole thing flat, right? Imagine that this is the top lid of a box. You lift this thing up, lift that lid so that it's in line with this front face. And now if the ant is going to travel from X to Y in the shortest possible way, it has to travel on a straight line. The straight line is the shortest distance between 2 points. So this path from X to Y is a straight line if you lift this top face up. And this angle 1 here, there it is, it's here. Because I'm just simply lifting it up, the angle doesn't change. Right? And here too, this angle doesn't change. So therefore, the shortest path will have the property that the 1 plus 2 will be 180 degrees. So the 2 angles at A, let's call them A1 plus A2, is 180 degrees. You can come to that conclusion because you know it's the shortest path. All right. So likewise now, you can say these 2 angles here, the 1 and 2, they add up to 180, and those 2 add up to 180. So how does it help us? We know when you add these, you get 180. You add these, you get 180. You add those, you get 180. So how does it help us to work out what X plus Y plus Z is? Well, let's analyze this again. You got that X, 1 and 2 are 3 angles of a quadrilateral. The 4th angle, we know what it is because you got a cube here, you see? So this is 90 degrees here. So we know what the 4th angle of that quadrilateral is. And likewise, in this quadrilateral, we know what the 4th angle is. And in this quadrilateral here, you know what the 4th angle is. So we can add up all the angles of all 3 quadrilaterals. Each quadrilateral has got 4 angles. So if you add all the 4 angles for each quadrilateral, you're going to get 12 angles altogether. Suppose I add up all 12 angles. Right? Amongst those angles, you've got X, Y, and Z. Right? This is one angle. Right, 3 down, 9 to go because there are 12 angles altogether. Now, we know those two, and those two. So you got, we're adding up all the angles of the three quadrilaterals. So you got 3 times 180 degrees, because each pair adds up to 180. Right. So now that takes care of 9 angles. There's 3 X, Y, and Z. And the 2 here, 2 here, 2 here, 3, the 6, 9. You still got 3 more to go. And those 3 angles are precisely these 3 angles here, which are all 90 degrees. So you have 3 times 90 degrees. Now, what is this? This is equal to the sum of all 12 angles. But wait a minute. The sum of the angles of any quadrilateral, we know. If you got any quadrilateral, you're going to have the sum of the 4 angles in a quadrilateral are 360 degrees. So it's 360 plus 360 plus 360, or 3 times 360. So now you got all the numbers except x plus y plus z. So you can make x plus y plus z the subject of the formula. You'll have 3 times 360, which is 1080. And you bring all the others to the other side, you get minus 3 times 180, so 540, minus 3 times 90. And there it is. You get something, I think you're 270 degrees. So you can actually calculate the sum of x, y, and z. Even if you don't know what x, y, and z are, their sum is always going to be the same, provided the end takes the shortest distance between any 2 of those points. Okay, so that takes me to the next problem. If you got any questions, you can put them in your chat column. Unfortunately, we are now, with 7 minutes left, and we are at the last problem. So, despite the slow start, we managed to finish this session. Now, this is a very interesting problem. Determine the integer value of this minus that. Now, of course, many of you will use your calculators to work out the difference and work out the square root. But I'm not sure whether the calculators will give you an answer, because you've got a 12-digit number here. If you take a 12-digit number and you subtract a 6-digit number like this, I think you will still get a 12-digit number. And when you work out the square root using the calculator, I'm sure you got some decimal points. Well, I'm not sure. I don't know. I don't hardly ever use a calculator. But it may give you an answer. So, but we're not allowed to use a calculator. That's the tragedy of these Olympiad problems. So you have to figure out some clever way of doing this without using a calculator. All right, so the first thing we notice is that you got lots of 4s and you got lots of 8s. And those 8s on the right-hand side there is actually related to this, because it's twice 444, 444. Right. So this is the first thing you notice. You say, but wait a minute, it's the same symbol that is occurring all over here. This number here, 444, 444. Right? So why don't we give a name to this number here? It's occurring in many places. Okay, even if you don't give it a name, suppose we don't complicate this thing, and we say we say this equals, we have a square root. Oh, let me Okay, let's avoid the square root for the moment. We'll try to simplify what's inside and then find the square root. So we take the inside and we're going to rewrite this inside so that all the 4s are nicely exposed. So what do I mean by that? That all the 4s are nicely exposed. So the first number is, we're looking at this number here. The 12 4s. Right? Minus 888. Right. If I just bring in the 4s, now this is 444, 444, and you can put 6 zeros here. I'm going to isolate the last 6 4s because I know that this is minus 2 times. All right, so now you've got this number here, 444. The number with 6 4s in it, 444,444, repeated 3 times. So a nice trick in mathematics is don't work with all these monsters. Just give it a nice name. And later on, you'll rename it. So you take this monstrous object here and you say that this is really x multiplied by 10 to the power of 6. Because this is 444 times 10 to the power of 6. So we're calling that x. And this is 1x here. So that's just x. And here you got 2x. So now we're kind of taming the monster here. X minus 2x is minus x. Right. This part here can be simplified. But now x is a common factor. You see the power of algebra. X is a common factor. So x goes into this, that. You can take it out. And we know what this is. That is, I'm going to replace the x now by 444 minus, no, these are being multiplied here. So we have written this thing because we factorized it, right? We took out the x. So now we have a factorization of that. So these things are now, oh. So this last thing that we got is 444. I've substituted for x. This number here is 1 less than a million. That's 999,999. It's another 6-digit number. All right. Now that tells me that I got, this is 4 times 111, 111, right, times 9 times 111, 111. So now I've got the trips, this number here repeated. And this is the final simplification of whatever we had inside here. But now you got 4 times 9, by the way, is 36. And this is 111 squared because it's coming up twice. And we asked to find the square root of that. So the square root of this can be immediately worked out because the square root of this product, it's a product now, you see. So you can take the square root of the product is the square root of each one of them, 6. And the square root of that is 111, 111, and that is 666. So without a calculator, you can say the answer is 666. And to get to that, we saw the power of algebra. factorization, all this that you do, you found a nice, useful application of something which you never found a decent application. And that, ladies and gentlemen, is the end of this session. Okay, I can entertain over to David. David?
Hi, Prof.
Yes. Maybe you can unmute them, and if we can see if some hands go up, and we can quickly just see what they have to ask.
No,
We'll allow 3 or 4 minutes for that.
yeah.
So unmute all.
No, they can unmute themselves. I don't know how to unmute all. I know
Okay.
how to mute all, but I can.
Okay, you can. Okay, you can unmute yourselves, and then. I can. Somebody is talking, but I don't know whether that's a question.
Prof is ready to take questions. If you have any question, you can ask or raise your hand.
Okay, that's fine. You could have. There are a couple of things on the chat, but you can place your question on chat now before we end the session, and we can address it at some other stage.
Yes.
Okay, so guys, thank you very much